In a previous video, I went over a few of the countless limitations involved with citing sources, which has become a bit of a controversial topic, because as a society, for whatever reason, we've seemingly adopted a cult-like fanaticism when it comes to believing anything we see online that has the thinnest veneer of authority. And that's unfortunate, because I don't know how you can convince yourself that that's a good thing. Regardless of what position you hold on any given issue, regardless of where you stand politically, you've probably seen people on the opposing side sharing infographics, statistics, papers, and various other sources. That's because so long as we have this belief that academia is this pure and untainted thing, then who safeguards academia? Will it be the people who shout loudest for your dollar and your vote, declaring themselves to be the academics? Because if you say, oh, well, the true academics, they'll be the ones who hold the line and fight for intellectual integrity, telling us what to believe and what's a lie, then that still only raises the question of how, when the imposters do the same and tell us that the academics are lying to us, how will we tell them apart? Ultimately, as always, you. You are the last line of defense against those who want to manipulate you. You can either choose to be skeptical, which is what I often encourage people to do, going as far as to tell people that if you can avoid using sources in an argument, then don't use sources. However, of course, that's a bit idealistic. Not to mention other people are still going to use sources, so it's important to know how to interpret information for yourself in order to combat that misinformation. So with all of that being said, I want to not only continue the theme of the previous video, but a bit more optimistically this time. I want to go ahead and give you guys a bit of a crash course on how to read a graph, especially since I looked up how to read a graph here on YouTube, because I figured, oh, well, I probably couldn't do a better job than, all these other videos that are going to be out there. And like the best I could find is a speaker that's kind of Dora the Explorer-esque, just going, can you tell me what the highest point on this graph is? Very good. So right away, if that isn't any indication, I'm going to skip over the very basics. I mean, I guess, in case you do need to hear it explained, this is a graph. You read it left to right. There are going to be values at the bottom that correspond to values on the side. This is just one style of graph. There are different kinds of graphs. But typically something like a pie graph is going to be used to represent demographics and compositions. And what I want to focus on in this video are the more intermediate lessons on how to read a graph that represents the effect of an independent variable on a dependent variable. So getting to that, as you may know, there are three terms used to describe the broad trends that a graph or a portion of a graph can have. If increasing the independent variable, the input or the x value, seems to increase the dependent variable, then this is called positive correlation. If x goes up but y goes down, that is called negative correlation. And of course, if x goes up but y stays the same, that is no correlation. I'm not going to get you guys caught up too much in terminology, but just something of note here. When mathematicians name something, they generally do so very literally. Positive and negative don't mean good or bad, because it's not as though the graph is a sentient thing that knows what kind of information you put into it. So hopefully this should be obvious, but for example, if we work in pharmaceuticals and we're testing an experimental drug, a positive correlation between those who take the pill and those who died during our study, that isn't a good thing. So just be mindful about terminology, and as we'll emphasize later, keep in mind what is the context, because it is impossible to meaningfully interpret a graph without context. For example, I could show you three graphs on a linear downward trend. If I showed you only a portion of these graphs, I could get you to concede that they are all the same. However, if I showed you what was the complete graph for each, then you would see that only two of them are the same. But even then, I'm omitting the context behind these graphs. Maybe these three graphs represent the alleged effect over time of a given policy implemented in three different nations. If that's the case, then clearly, yes, this one nation started out with a higher variable than the other two nations, and these other two nations started out the same and changed at the same time, but we're actually still missing something in order to conclude that these are the same. If we have whatever variable we are measuring on one axis of the graph and time on the other axis, then we haven't actually told ourselves what kind of change is happening. More specifically, we haven't clarified if the change in policy correlates to the change in the graph. If, for example, these two similar nations limitations implemented the same policy at different times, we may say that we see a correlation, or none at all. And now, not to just blatantly insult you here if you don't know this next part, but hopefully if you have any common sense, you should understand that we can't just look at the height of a graph in order to read the relationship between an independent variable and its effects on a dependent variable. As we'll come back to, yes, it can at times be far more complex than this, but if, for example, you have two graphs where one starts out at 10 and one starts out at 4, if they decrease to 5 and 3 after some event, yes, 3 is lower than 5, but 5 is half of 10. So just based on that aspect alone, if these two graphs represent some implementation of policy, the graph that started out at 10 may be the better policy if the aim is to lower this other variable over time. 10 to 5 represents the greater change. I'm sorry if that was mind-numbingly obvious, but as I just promised, later we'll come back to how there's a little bit more nuance to it than that. But for now, obviously, the point we've arrived at is that the key to reading a graph is change. If, for a level graph, the graph goes up immediately after a point of change, then clearly this point of change, whatever it may have caused the graph to increase. Obviously, the same follows for if it were to decrease. I think it only really starts to get tricky when we consider that not all graphs are going to be flat lines. For a graph on an upward trend, if something is enacted here, and for the sake of this video, we know that it had an effect, did it correlate to an increase in the dependent variable or a decrease? Well, you may be tempted to notice that the graph is higher after the change, but this is what I mean about thinking rather simplistically in terms of high or low rather than in terms of change. Yes, the graph is higher after the change, but assuming the graph would have carried on its trajectory prior to the change, which obviously for the sake of this example it would have, then we see that this point actually resulted in a decrease of this trend. If this was, for example, some political policy being enacted that was supposed to reduce unemployment rates. Whether this policy worked can become a matter of interpretation because, yes, it didn't decrease unemployment rates in the most literal sense, but it did slow the rate of growing unemployment and decreased it from what it would have been otherwise, which means that this policy did in fact have a positive effect. Positive as in good, not positive as in, or is it this way? I'm used to a camera that mirrors me, so you get the point. When we look at the change in a graph, the best way to envision it is as if there were a line at whatever point we are looking at that continues indefinitely forwards and backwards in the direction of where the graph would have gone if it did not change. This line is the tangent line of the graph at a given point. If you were to take the slope of a tangent line at a given point, then that would tell you the derivative at that point. And I know I promised minimal math in this video, so let's try to make this as painless as possible. Just as you would say that a hill has a higher slope the steeper it is, the steeper the line, the higher the slope. This is a slope of 1, 2, 4, and 16. A slope of 0, of course, looks like this, and negative numbers go down instead of up. So all you really have to do is move the tangent line across the graph and look at the line. Here it looks like -2, here it's in between -1 and 0, here it's clearly 0, and so on. It doesn't have to be perfect, but if you can get to the point where you kind of see the derivative of the graph, you're going to be able to understand it a lot better. Because in this context, the derivative graph is just the change of the original graph over time. It represents the rate of change. If you were measuring the distance of an object over time in a physics problem, for example, the derivative of that graph would be the velocity of the object, and the derivative of that object's velocity would be its acceleration. That obviously has very little to do with graphs in a political or philosophical landscape, but it's just good trivia knowledge. Also, fun fact, the names of the next derivatives are jerk, which who cares, but then you have snap, crackle, and pop. I'm not kidding. Like, come on, aren't you glad that you now have this completely pointless knowledge? Us math lovers, we aren't completely boring. We have fun every once in a while. Jokes aside, well, it's not a joke, those literally are the names, but that aside, being able to visualize the rate of change for a graph can be very helpful. Take, for example, the graph we made up earlier for unemployment rates. Here we can see that the graph prior to the change has a constant slope, and so we get a constant number. But as the policy is enacted, we see the graph dip down before returning to a constant number. Here, more clearly, we can see the reduction of the rate of the homelessness rate over time. And I know that may have been a lot of work for something that most of you could probably see already. but this is just where I have to offer one of several jumping off points because it's just something you may find helpful in interpreting graphs. I certainly do, so if you're interested in that, I would recommend researching further. In statistical analysis, you may use derivatives to find the extremes of graph to know when it's changing the most. You may use it for inflection points or just in general as a tool to generalize and predict trends. However, I don't want this video to go too in depth, so what do we know so far? How do we read a graph? Look for change, specifically rate of change, which we can use derivatives to visualize, but how do we visualize the responsibility of one variable on another, or even other variables? Here's what I mean by responsibility. When we look at this graph, we now understand that the implementation of this policy changed the rate at which unemployment increased. But whether you think of this line as having some sort of momentum or being continuously driven by some factor, it's clear that it's still increasing and that something has been causing it to increase even before our policy was enacted. Not only in life are you rarely going to have straight flat lines, but you're also going to be scarce to find an instance in which one thing in isolation acts on another. So when we implement a policy, how do we know that it was our policy that led to a change in the graph rather than just a change that would have happened otherwise? Well, here is why I'm often super critical of empirical schools of thought. You can't. At least, not always. In some circumstances, for example, in a more rigorous scientific setting, you may have control groups where you omit your dependent variable in order to have a baseline to compare your experimental group to. Or, even better, you may be able to just completely create a perfectly controlled environment in which you know that all you are measuring is your independent variable and your dependent variable. But that's all just hypothetical. Yes, for the natural sciences like chemistry and physics, that tends to be how it goes. And I suppose I should mention that one could make the argument that there is still room for error in that you can't have a 100% perfectly controlled environment, but depending on the context, that can be needlessly nitpicky. If we know something with 99.999% certainty, we might as well say that we know it with absolute certainty. But with softer sciences, like the ones that typically find themselves at the forefront of political debate, like sociology or psychology, this just isn't as easy. People are different, having different lives, different experiences. How do you account for that? And in some of these experiments, how do you ethically have a control group or experimental group? If you're testing the effects of abuse on children, do you go around beating up kids? Point is, far too many people ignore how less conclusive a study is when it lacks physical controls. I mean, don't get me wrong, there are ways to logically and mathematically account for this. Perhaps the most obvious would be to sort of brute force your way through it and observe if there is a frequent correlation between a given cause and a desired effect across instances in the presence of other variables or covariables. However, this can only really work when you have large sample sizes, because you need to see that each and every time something occurred, no matter how much all of your other measurable variables changed, that your cause led to its desired effect. If not, then we may be led to ask if there is a trend in your graph corresponding to other variables in the few instances in which the expected correlation was not present. If so, we may have to say that, for example, yes, the implementation of A may reduce X by a given amount, but only when B is not present. And that all could obviously lead to several questions for other graphs and would depend almost entirely on the context of the graph. If someone thinks that gun control, for example, works in other nations, but only these nations with very disciplined cultures, is it the gun control that is working, or is it the culture that is working? Do two variables add, multiply, or otherwise operate together to lead to a certain effect in a numerical sense, or do they affect each other in a more qualitative way? That's a lot to cover, so by virtue of that, I'm not going to try to cover it. Instead, I want to just go back to something I said earlier and double down on the harsh truth that a lot of science LARPers are not going to like. Even if you can isolate a variable accounting for all other covariables, and even if you have an exhaustive sample size where correlation is shown time and time again, even if you have done all of that, you have still only shown that something may cause something else, because that is still by definition an inductive argument. You are taking one example or several and inferring a general rule about how one thing acts on another in all other instances. Going from specific to general, that is inductive reasoning. The issue with that is that this sort of reasoning can only prove that things are likely to be true, but it can never prove that things are true with absolute certainty. If I ask you to judge whether or not a coin I am flipping is fair, one flip is definitely not enough to prove it. If I flip heads twice, you may be skeptical, but likely you'd understand the sample size is just too small to conclude anything yet. But how long would I have to keep going? Pause this video, go to Google, search flip a coin. What's the most you can get in a row? 2, 4 maybe? If my coin landed on heads 8 times in a row, would you think it did so legitimately? Well, if you're a smart aleck and you understand what a teaching aid is, you know the answer is yes, it is possible. In the Guinness Book of World Records, the highest recorded consecutive heads was 8 times, which doesn't really seem like much, and theoretically, there is no upper bound. You could flip a coin and have it land heads infinitely many times because it's not as though the universe cuts you off on a lucky streak. It just becomes more and more unlikely until it is practically impossible. And an issue here is that there's no real singular point of practical impossibility, because as the name implies, it has to do with the practical application of information. If you have a 99% chance to win $100, but there's a 1% chance you'll lose $1, that's good odds. However, if now instead you have a 1% chance to die, suddenly the game becomes a lot less worth it. That isn't to say that, for example, with larger sample sizes, that correlative arguments cannot prove that something may or is likely even to be true. It's just that it's not the end-all be-all of an argument. Like, it's frustrating to see person A offer up 5 examples of a policy working, and then person B offers up 10 examples of a policy working, plus a counter-argument to person A's policy. But then, because person A has this preconceived notion that quantitative data is better, he just acts as though person B is an idiot, even though he provided better arguments, more arguments, and a counterexample, simply because his arguments are qualitative instead of quantitative. Which, by the way, is the McNamara fallacy. There's a name for it. Because it doesn't matter if it is qualitative or quantitative, correlation is correlation, and correlation is pretty weak as far as arguments go. And this is why, as I mentioned earlier, controls are used. If we say B is caused by A, and then conclude that because B is present, A must also be present, this is affirming the consequent, a formal fallacy. The issue here is that we don't know if A is the only cause of B. Just like how in a correlative study, we don't know if other variables may be influencing the outcome. So the more philosophical explanation of controls is that they are used to bridge the gap between inductive reasoning and deductive reasoning, turning what is otherwise a fallacy into a valid argument. Yes, affirming the consequent is a fallacy, but a statement like A is the only cause of B, B is present, therefore A is present, must necessarily be true. So intuitively, controls aim to limit the number of causes such that only A can cause B. And so if B is observed when we introduce A, we can conclude that our hypothesis of A causes B must necessarily be true. Now, I understand that it probably just sounds like I'm repeating what I said earlier, but in a more philosophical way. But as obvious as what I just said may be, it's necessary to understand it in this way in order to understand its implications. Obviously, as I mentioned earlier, some people question whether or not we can be sure that we have just A in isolation. This is where the skepticism in even the strongest studies comes from, where some say, oh, well, that's just a theory. But I would say that that skepticism is a bit misplaced, because it could apply to even the most mundane of observations. How do you know that you exist? How do you know that the world exists? It's generally just a level of scrutiny that is driven by personal bias. However, as we can see, there are still limitations to this method. You have to go through all of this effort in order to make sure that one thing logically implies another. I, on the other hand, do not have to do the same. If you say A causes B because A and B are in an isolated system where only A can cause B, then completely undermining your argument is as easy as proving that A is not the only variable in the system. I don't even need to prove that C, for example, causes B, because your ability to make an argument that resembled a strong deductive argument was predicated on the fact that B could only have one cause. This means even if you still have a strong argument for why A causes B, it still becomes weaker, essentially becoming more inductive. And with an inductive argument, you have to accept the likelihood of your claim. If you say A causes B, or that B will always happen when A is implemented, you are technically wrong. At best, A may cause B. And for instances in your data where correlation is not shown, I can correctly point out that A could not have caused B in those instances. And for each variable that is introduced into the system, if you didn't have a strong inductive argument, and if, for example, you were just guessing, you could imagine how with 2 possible causes, you would have a 50% chance of being right. With 4 causes, that goes down to 25%. And obviously that just keeps going down and down. If you have any doubt in your argument, which you should if you are making an inductive argument since they cannot deal uncertainty, then your uncertainty is only compounded when there are more variables in the system. You don't need to be very certain when you already have a 50-50 chance, but with more variables, more certainty is required. Which is why I just want to emphasize that studies that use controls, like in physics or chemistry, good. Studies that just look at correlation and nothing else, those are garbage. You can't just hope that correlation means causation, especially when you're looking at raw data that rarely, if ever, correlates. Although it is worth mentioning that, obviously in the field of statistical analysis, we don't just have to look at raw data like I've been showing you. Let's imagine that you have a jar and I give you $1 a day, but you also get an unspecified amount of money from someone else. This means that the sum of the jar each day is the sum of all of the money that I have given you plus the sum of the money that this other person has given you. If we want to figure out the amount that this other person donates each day in the running sum, then all we have to do is subtract my sum. When we look at this on a graph, my donations make a line that increases one at a time. So subtracting my sum is a lot like just shearing the graph by this line. This is a linear transformation of data that you will often see in research papers. The purpose is to adjust for a given covariable or covariables. In effect, this is a lot like controlling for these variables. However, the limitations are far greater than we would expect if we were using traditional controls. For example, obviously in this instance, we knew that I was the other variable, and we knew the exact amount I was contributing each day. If we didn't know this, we would have to find a way to estimate, predict, or project the covariable. And if, for example, I donated a random amount each day, the need for such an estimate would become even more apparent. Because let's say that each day I donate $1 or $2 at random, but you don't know anything more than that. You would only really have two options. One, you could take an average and say that I donate $1.50 each day. Or two, if my donations are truly random, you could consider the full range of my possible donations. First, imagine the $1.50 estimate. Over the course of 4 days, if you know that these are the collective sums, you would say that I, of course, donated $1.50 each day, and that this other person therefore donated $6 in total. Now, if I show you the actual numbers, you may fight me on whether these are actual numbers, because obviously you could argue that I can pick whatever numbers I feel like for this example. However, as we'll get to, this arrangement is actually just as likely as any other, and the sum is not improbable or unlikely. In this instance, the actual total the other person gave was 7, meaning that our estimate has a 14% error. That may not sound like a lot, and again, the acceptable amount of percent error greatly depends on context, but for example, a high school chemistry teacher will usually expect anywhere from 5 to 10% error from his students during a lab experiment. So we did objectively worse than a high schooler. Not to mention, that's only for the total. If you had to predict the amount this other person gave on any given day, your guesses would range from 16 to 50% error. Are you starting to get the point? We can isolate variables in a way where we can make really good, educated guesses, but they're always just going to be that. Guesses. Even and especially if we take a more thorough approach like analyzing the range of possible outcomes. If I donate $1 or $2 randomly, here is every possible permutation of events. There is one event where my sum is 4 and my average is 1, 4 where it is 5 and 1.25, 6 where it's 6 and 1.5, 4 where it is 7 and 1.75, and 1 where it is 8 and 2. This means that with the averaging method we used earlier, for all instances, there was a 60% chance to get a percent error of 14 or worse for the total sum prediction of the other person. And for daily donations, we can only really conclude that there's a 37.5% chance he donated 6 in total, 25% chance he donated 5 or 7, and 6.25% chance he donated 4 or 8. Also, as counterintuitive as this seems to be for some people, if these events are truly random, none of these events are more likely than the others. Every event has a 1 out of 16 chance of occurring, meaning there is no way to more accurately predict the daily sums. If, for example, we knew that the sum of day 1 was 3, I could have given 1, or I could have given 2. And each event was equally likely since it was random, meaning we would have no way of knowing whether the other person gave 1 or 2. In more complex situations, like rolling 2 dice, we may be able to make more meaningful probabilistic inferences. For example, if someone rolls a 12, it can only be the case that they rolled 2 6s. Likewise, a 10 can only be rolled from a handful of permutations. But ultimately, no matter what situation you envision, probabilistic analysis is always going to be just that. probabilistic. It loses its prescriptive quality, especially in politics, for example. If you tell me that a policy has a 70% chance of working, what does that even mean? Also, aside from perhaps on the quantum level, we don't live in a world of probability. A coin flip will obey the laws of physics, dice too. Nothing is truly random, and even if it were, this more often than not comes back to thwart statistical analysis. If the amount of homelessness in a region can vary by 10,000 seemingly at quote-unquote random, then any policy enacted that is said to have decreased the amount by less than that is statistically meaningless, because there is no way to know whether the policy caused the change or if it was just expected variance. And if we view variance not as a truly random thing, but as a cacophony of unknown causes, then therein lies the problem. The causes are unknown. Maybe I donated what I did to your jar because I flipped a coin, or maybe I used to donate $2, but because of recent economic struggles, I started a trend of only donating $1. Or maybe it's just a change in my personality. We don't know. And we can't know until we explore these questions qualitatively, not quantitatively. For example, at the beginning of this video, I said that we need to look at change, but what if a large change from a higher number, like 10 to 5, is only because it is a situation in which decreasing from a higher number is easier, meaning the change isn't all too meaningful? For example, in high school track and field, I used to run the 400, and I reduced my original time by 30%. But that's only because I started out running terribly at like 70 plus seconds and eventually worked my way down to a 55. That's not too impressive, that's like slightly above average. But if I dropped 30% off of my current record, I would break the world record. This is because human endurance has a limit, just as other concepts may have limits. And likewise, if you were to chart the speed of someone over the course of years trained, the graph would not plot out a simple line. It would follow a curve more like this. So if you were to plot a linear predictor given 2 early points, you would end up at a laughable conclusion. The only way to know the behavior of the graph in order to predict it is to understand the very nature of the context behind the graph. If you go back to the jar example, when you knew how much I donated, you could know with certainty how much the other person donated. When you didn't know how much I donated, you had no way of knowing how much he donated. When it comes down to knowing the variance, the limits of a trend, or anything else about a graph, that is ultimately about knowing the context of that graph, which hopefully you can see makes the graph entirely unnecessary. In order to know what variables to account for quantitatively, you have to know how they affect your dependent variable qualitatively. And so this desperate urge to give specific arguments, this academic authority of being statistically verified, makes no sense. You can't just act as though quantitative information is far more objective, as if we live in a quantitative world. As if nobody ever had to go out and observe the world qualitatively and make a personal judgment on how to represent that information quantitatively. And even after that, as if there are no personal judgments made about whether or not a variable is actually isolated. No personal judgments are made on what is the best way to isolate the variable. And as if no personal judgments are made on what is statistically meaningful. I am not saying this as someone who hates math. I love math. I could just as easily sit here and use my understanding of math in order to gatekeep arguments and to gaslight people into agreeing with me. But the honest, harsh truth is that statistical analysis should really have no place in something as contextual as politics. The admiration of empirical study just really comes down to this primitive desire to live in a simplistic world and use statistical analysis as our ancestors would have used dowsing rods for water. But numbers are not tools of divination. They are just abstractions. They are a way to represent information that may be helpful for some purposes, but not for all purposes. And as abstractions, they are never more objective than the qualitative information that they represent. So, trust statistics at your own discretion. I'm not going to tell you that empirical study has no place in the ongoing search for truth, but it's just clear that society has turned this once great tool into a dangerous weapon. And if you didn't before, hopefully now you know how to defend yourself against this weapon.